Hello guys, this is Code and Code, and this is first lecture of this number theory series. And in this lecture we are going to study about primality test. So let's start the lecture. So first of all, what is primality test? Primality test is to determine whether the given integer is a prime number or not. So suppose the input is 5, so the output should be true because 5 is a prime number, while if the input is not a prime number, of course the output would be false. So first of all, the naive approach or ad hoc or brute force approach would be to run a loop from 2 to less than n, that is 2 to n minus 1. If the number is already 1, we would return false because 1 is neither prime nor a composite number, so it is not a prime, so we would return false. Otherwise we would run a loop from 1 to less than n and see if any of I divides the number n. If it divides, then we would return false, otherwise we would return true. So the complexity, if you see, of this algorithm is big O of n, that is linear. So let's try to improve upon this running time of the algorithm. So a better approach towards the better approach, let's learn something about the pairs. So for each number n, the divisors of number n occur in pairs such that a multiplied by b is equals to n. So if you take an example of 12, the divisors of 12 are 1, 2, 3, 4, 6 and 12, which you can form the pairs as 1, 12, 2, 6 and 3, 4. If you see, multiplication of each pair is equal to 12. 3 times 4, 2 times 6, 1 times 12. Now why we are studying about pairs is that, you see, if you find one element of a pair, you don't have to find the other. You can simply find other by using one element of the pair. So if you have 1, what is the another element of this pair? Of course it is 12 by 1, that is 12. Now if you have 2, the other member of this pair is 12 by 2, that is 6. If you have 3, the other member of this pair is 12 by 3, that is 4. So you see, if in this case all you have to do is run a loop from 1 to 3 only, you don't have to go beyond 3. So if you have one element of a pair, you can find another, and using that fact, we see for this example all we have to do is run a loop from 1 to 3, not above that, because from 1 to 3, whenever we get a divisor, we simply divide n by that number and then we get the another divisor. But the problem is 3 is limit for 12. How to get the limit for each number n? Because for 15 you may have to run a loop above 3, up to above 3, but you have no idea what is the limit till which you have to run the loop. So let's find what is the limit of that n of any number n, such that we have to run loop from 1 to that limit, not completely till n. So you see, the claim is for a divisor pair AB, one of them lies below square root of n and another one lies above square root of n. So to prove this claim, we can divide the proof in 3 cases. First, a and b both are below square root of n, a and b both are above square root of n, and of course the third case would be this. And since we are claiming that this is true, hence case 1 and case 2 should be wrong. So let's prove this. First take this case 1, where both a and b are below square root of n. So we would prove it by contradiction. So let's assume that this statement, that is case 1, is true. Hence a is less than square root of n and b is less than square root of n. But if this holds, then a multiplied by b would be less than n, which contradicts our statement that a and b are equal to n. And we reach this contradiction because the assumption that we made is actually wrong. Hence this is not true, this statement is actually false. Now let's prove case 2. Now we would prove case 2 using the same argument that we did before. So let's assume that case 2 is actually true. If that's the case, then a would be greater than square root of n, and so would be b. But then if that's true, a into b would be greater than n, which again contradicts our statement or the fact that a into b is equals to n. And we reach this contradiction because the assumption that we made is actually wrong. Hence case 2 is also not true. To prove case 3, that is one is below square root of n and another one is above square root of n, we would prove it directly. We would use direct proof to prove this. We can write a as square root of n multiplied by square root of n divided by b, right? So subcase 1 is when b is less than square root of a, or square root of n. If b is below square root of n, then a should be above square root of n, of course. If b is below square root of n, which would give square root of n divided by b would be greater than 1. And hence I can write square root of n divided by b as 1 plus x, since square root of n divided by b is greater than 1. And if you expand it, you would get a is equals to square root of n plus x into square root of n, which directly shows that a is greater than square root of n. So see, we taken a b smaller than square root of n, then a comes out to be greater than square root of n. Same goes for this. If we assume a to be square root of n or greater than square root of n, then square root of n divided by b would be smaller than 1. Since square root of n divided by b is smaller than 1, then I can write it as 1 minus x. So if I put this value 1 minus x into this equation, it would become a is equals to square root of n multiplied by 1 minus x, which certainly would be a would come out to be this, that a is smaller than square root of n, because if you expand it, you would get square root of n minus x into square root of n, and hence a would be smaller than square root of n. So if you are taking b smaller than square root of n, then a is coming out to be greater than square root of n, and if you are taking b as greater than square root of n, then a is coming out to be smaller than square root of n. Hence we have proved that case 3 is actually true using direct proof. Now using this fact, we know that in a pair one element is always below square root of n, or below or equal to square root of n if the number is actually perfect square. So now since suppose 25, so square root of 25 is 5, so the pair element of 5 would be 25 divided by 5, that is 5. So pair would be 5 comma 5. So we can see if number n is perfect square, then both the divisor element of one pair lies on square root of n, otherwise all lie below square root of n and above square root of n. So since now we have two facts. Fact 1, if you find one element of a pair, you don't have to find another, because you can simply calculate it. You don't have to find, you can simply calculate it. If you find one element to be 5, you can simply divide n divided by 5 and you get your another element. Now second is that one of them lies always below or up to equal to square root of n. So this gives us the upper bound, so we don't have to go above square root of n. We can run a loop till square root of n and find all the divisors. So you see 1, 2 and 3, all of these elements which lie below square root of n for 12, because square root of 12 would be 3 point something something. So 1, 2 and 3, all these 3 lie below square root of n. So we don't have to go above 3. We can run a loop till 3 and we would find all the divisors. So to check whether a number is divisible, is a prime number or not, all we have to do is run a loop till square root of n. If there is a divisor, then we can find it till square root of n. We don't have to go above. And if we don't find any divisor till square root of n, then the number is actually a prime number. So how we can modify the solution is prime? If n is equals to 1, we would return false. Otherwise we would run a loop from 2 to square root of n, and since I square is less than equals to n, hence I would be less than equals to square root of n. So if I into I is less than or equals to n, that is we are checking whether we are running a loop till square root of n or not. So basically we are running a loop from 2 to square root of n, and if number is divisible by if number n is divisible by n, then answer is 0. Oh sorry, if n is divisible by I, then we would return false because we have found a divisor. Otherwise, if after running all through all this loop we don't find any divisor, hence the number is actually prime number. So what is the complexity? Of course the loop is running from 2 to square root of n, hence the complexity is square root of n. So now we see we started from naive algorithm which was running in big O of n time. Now we have modified that solution using little bit of mathematics, and now we have a solution which runs in square root of n time. Try to play with this using pen and paper, and you would this would get into your head easily. So till the next video drops, I'll be taking 3, 4 or 2 or 3 practice problems to apply this algorithm. So till then, yep, keep coding and keep playing with this thing.